In step one, we close switch one, and we allow the system to come to equilibrium. Now, you guys should have no difficulty figuring out what the potential difference and charge is across this capacitor. The potential difference is 12 volts. That's obvious. Charge on the capacitor, just use the definition of capacitance. So Q equals CV. So it'll be the product of those two. So 600 microcoulombs. We do our arithmetic correctly? All right. Now, we open switch one. Does anything happen to that capacitor when we open switch one? No. Assuming it's an ideal capacitor, it stays charged. But when we close switch two, I assume you agree something's going to happen, right? Now, here's the big question. The 100 microfarad capacitor is uncharged. So at time zero or time whatever, when we close the switch, chargers are probably going to move to begin to charge up that capacitor. But I want to remind you, this can be solved a different way. This can be V equals Q over C. Correct? Any amount of charge that leaves the 50 microfarad capacitor reduces the potential difference across that capacitor, right? As charges leave it and the capacitance doesn't change, the voltage across that capacitor is also going to decrease. However, what drives the charges to move in the first place is potential difference. If you've been paying attention, this one's tough. If you've been paying attention, these two capacitors will be in parallel and will need to come to equilibrium. The equilibrium is going to occur when both capacitors are at the same potential difference. Until that time, if there's a difference in potential between the two, charges will move until the potential gets the same. So although this is the initial conditions of our circuit, there is a future condition. I'm just going to draw a separate set here. A future condition where the 50 microfarad and 100 microfarad come to some form of equilibrium. They're in parallel, so the voltage across these two capacitors will have to be the same. And from the argument I just made, I think you would have to surmise that it's less than 12 volts. It would have to be less than 12 volts because charge is going to leave the 50 microfarad capacitor. And if charge leaves the 50 microfarad capacitor, its potential difference goes down. Now here's the part that I think might be hard for you guys to put together, even though it's not new. In this portion of the circuit, after switch one is open, that whole section is isolated, which means we can get no new charges from the battery. So whatever amount of charge we have on the 50 microfarad capacitor is all the charges we have to work with. Right, that's Kirchhoff's second law. So the charge on this capacitor and the charge on this capacitor would have to sum to equal 600. Because there's a finite amount of charge. Now I've told you things. You should be able to use those things to figure out your answer. All right, so while you guys are thinking about it, I do have a couple people who couldn't get the answer. So let's talk a little bit about what had to be done. Q over the 50 plus Q on the 100 has to equal 600 microcoulombs. There's a finite amount of charge. But Q equals CV. This is also true. So 50 times V plus 100 times V has to equal 600 microcoulombs. The 50 and the 100 are both microfarads. So this gives me V equals 600 microcoulombs divided by 150 microfarads, which gives us our 4 volts. I think this is the easiest way to get to the answer. There are other ways you could have gotten to the answer. I think this is the easiest way. But you might have done something else. There's a whole ratio thing you could have done here too. So if you look up something on the internet and find something about ratios, enjoy. It works. But this gives you the voltage. Once you have the voltage, you can go backwards and get the charge. So again, CV. So my 4 volts times 50 gives us our 200 microcoulombs and 400 microcoulombs. But the question is now about energy. So when I ask about energy, that's a different question. So over here, the total energy in the circuit was 1/2 CV squared, or 1/2 times 50 times 12 squared. That's 3,600 joules. I'm sorry, microjoules. Do we have that many microjoules after the charges flow and we re-equalize? When I worked it out, the answer is no. I did 1/2 CV squared here and got 400 microjoules. And over here, I got 800 microjoules. This does not equal 3,600 microjoules. It took energy to redistribute those charges, to charge up the other capacitor. So moving those charges around took some energy. All good so far? Because we're not done. I think we've got done with part A. Are you ready for part B? We have a pretty solved circuit here, don't we? We know the voltage and the capacitance and the charge and the energy on each of our capacitors. So it seems like it's time to upend the problem and make it a little bit different. So consider this. When we are in this state, we take a dielectric and put it between the plates of one of the capacitors. Assume it has a dielectric constant of 4. I have 3 questions here, and I think you probably know what they are. What is the new amount of charge on each capacitor? What is the new voltage across each capacitor? And did we do positive work or negative work? Did we increase the energy of this system or decrease the energy of this system? By the way, no new rules. You can do this problem using the exact same rules we just had. So I don't think I need to help you. You do need to know that one of the capacitors' capacitance changed by a factor of 4. Give it a shot. This time I do think I can call on somebody here, and I think I can call on anybody because you guys who put your hands up and said you didn't know how to do the last one. This one should be okay. So this is no longer 50 microfarads. What is it? Yeah, it's 200. That shouldn't be tough, right? Dielectric constant of 4. So that just multiplies the total capacitance. It becomes 200 microfarads. So that's the change. You change that to 200 microfarads. But that means this amount of charge and this amount of charge are going to change. And it probably also means that this amount of energy and this amount of energy are going to change. And probably the voltage probably going to be gone too. But Q over the 200 plus Q over the 100 has to still equal how much? 600. What's next? Well, 200 microfarads times V plus 100 microfarads times V has to equal 600 microcoulombs. Come on, folks. This is not tough. This one's the easy stuff. The fact that you're writing it down so quickly tells me you didn't even get this far. So V equals 2 volts. Voltage drops again. It's weird, but it does. Not done yet. You got to figure out the new distribution of charge. But I bet, since this one's now twice as big as the other, that it's holding more of the charge. But you should check. Again, it comes down to Q on the 100 is going to be equal to 100 microfarads times 2 volts. So it now has 200 microcoulombs. And Q over the 200 has got to be 200 microfarads times the 2 volts. Now it's got 400 microcoulombs of charge. So we just pulled back some of the charges back to the other capacitor. We made it bigger. It can hold more. And so it will. Now for the energy, though. 1/2 CV squared. So 1/2 times 100 times 2 squared. That looks like 200 microjoules. This one, 1 times 200 times 2 squared. That looks like 400 microjoules. Did the energy go up or down? It went down again. Right? So, yeah. Total energy of the system was reduced. So it took work, took energy to push those charges back to the old capacitor. The work here isn't hard. All right, so, I mean, you see the similarity here, correct? Very similar circuit. So in this one, I'm thinking the same problem, the same exact question. I close switch 1. I let those 2 capacitors come up to a full charge. Then open switch 1 and close switch 2. Now, this one is not much more difficult to do if you understand that probably for you guys, the best way to deal with this one is to deal with the equivalent capacitance of those 2 that are in series. Like, work the problem not with the 500 and the 200, but work the problem with the equivalent capacitance. Do you guys see what I'm suggesting that you do? Okay. Now, I'm suggesting that, but then when it comes to the dielectric, I can only put it in one of those capacitors, right? So in the last example, there was only one capacitor there. But in this example, if I put it just the dielectric in the 50 microfarad, that's where it becomes a little more complicated. Do you guys see what I'm suggesting? So if you want, we can work this to its floration, or you could do it tonight and we work on it tomorrow so that you guys struggle with it. 2 people already shook their heads. It doesn't matter to me. It's your time. It's how you wish to spend your class time. So I'll give you the rest of the question. We close switch 1, let it get charged. Then when it's fully charged, open switch 1, close switch 2. Tell me what happens. Tell me about the charge, tell me about the energy, tell me about the potential. Then while switch 2 is closed, a dielectric of value of 4 is inserted into, pick your capacitor, doesn't matter to me. It's going to be the same amount of work. So we'll say put the dielectric in the 50 microfarad capacitor. What happens? It's a good question. It's solid. It's got all the stuff in it. I also stopped at this point. I thought it'd be appropriate to figure out the voltage on the individual capacitors because it would probably be asked. And that required figuring out what the charge is on the individual capacitors. I found it was 137 137 microcoulombs on each of these. The other side had, I wrote it down, 343 microcoulombs on this side. And then if you split out the voltage, you get, a portion of each. I think I still left that in my calculator, but you get your individual voltages across each, with this one being something like 2 point something volts and this one being under that. So it's in my 2.74 and 0.69. So those are the individual voltages. They have to calculate the total energy here. Now you can calculate the energy from the equivalent, and that works. So if you don't need the energy from the individuals, you can calculate it from the equivalent. And you're supposed to show, now we already know the total energy goes down and is going to go down again in our next step too. So you'll find less energy here. Now, when we come back to the next part of the circuit down there, we still have a finite amount of charge. Yes?